Okay, for today, I just want you to have a blank notability doc, and we're going to do a bunch of problems together. Ready? Okay, so the first one I want you to tackle is this one. I noticed that I hadn't really challenged you with some super hard fraction exponent problems yet, so I want you to see if you can make that into, here's why I would want you to do it. If you had log, here, I'll do that out here, log base 5/12 of all that, hopefully you'd be thinking to yourself, how can I make that have a base of 5/12? Okay, because then if it had a base of 5/12, it would look like this, log base 5/12 of 5/12 to the negative 5/6 or whatever it is. And then if this was the same as this, the answer would be that. That's why we're doing this. So we want to make this have a base of 5/12 and be a fraction exponent. All right, I'm going to pause for a second while you give that a try. You get
I got 5/12.
5/12 to the negative 2/3. Now, how could I test him? I could take this and say, what's the third root of 5? Whoa. What is the third root of 5? I have no idea. So I guess I could put it in a root and say third root of 5/12. Then, what's this 2 going to do to these guys? The 2 is going to flip them? No, the 2 isn't going to flip them. The negative would flip them. The 2 would do what to them? Square them. So now it's 25, and 12 squared is 144. And is that what I had? No. So the negative would then take this and flip it. It would make it 1 over that. Now, some people are like, wait a minute, what do you mean by 1 over that? 1 over that means you flip it. So inside its little root, it's still a cube root, it's going to flip and make 144 over 25. That's what happens when you take a fraction and you put 1 over it. Even if it's inside a root like that, it's okay. So bottom line, we figured out that your power of negative 2/3 was right. Raise your hand if you actually agreed and had negative 2/3 on that one. Good, that was a tough one. All right, here's a much easier one. Let's say that you've got this problem, 5 to the x plus 4 is equal to the square root, no, fifth root of 125. What would you be thinking about the bases here? You'd like to make them equal. And so how can you make this have a 5 to a power? Pause for a second while you guys figure out how to make that 5 to a power. Tell me what you got. Yep. That is a 5 cubed. I like that way to start. So I'm going to change this to a 5 cubed. 5 times 5 times 5. And then what?
Then you take the cube of 5 cubed to the power of 1/5.
That is a 1/5. Good. And if you're going to do 5 cubed to the power of 1/5, simplify it down for me. That is 5 to the... Yes. And this 3 is over 1. So it goes on the top. So that 5 and a 1 go on the bottom. So it's 3/5. You're right. Raise your hand if you had that one right. Awesome. And if this had been the problem, you would now say that equals that. Notice we aren't canceling the 5s, but we are just saying this exponent must be equal to that exponent. All right, cool. Another one. Let's say that again, you're in a problem like log base 4/5 of, and then they have this, square root of 64 over square root of 125. And you will say to yourself, I need to get that to be 4/5 to a power. Okay, let me pause for a second. Let me try that one. And I hope you started with 64 being 8 squared. No. What? 64 is really 4 to the 3rd. Now, how do you know you should use that? Because 8 wasn't in the fraction that I wanted. I wanted a 4 and a 5. This 125, aka 5 to the 3rd. Then I got to deal with the fact they both have square roots on them. So you can say this is 4 to the third over 5 to the third, and it's all in one big square root. You can just combine them like that. Final answer, 4/5 to the, that's a second root. The roots go on the bottom, just like in plants, but they also are being cubed, so I can put the 3 right there. 4/5 to the 3/2. Now, if I had done that, then all of this becomes 4/5 to the 3/2. And then why is that so good? Because the bases are equal. So then what's the answer? 3/2. This whole thing is equal to 3/2. So if I wanted to make a really complicated looking question, remember the answer to this comes out to 3/2. I could start with this. And really all of that is equal to 3/5. And then I could say 4 times that plus n is equal to 17. And that looks like the scariest problem in the world. But then, if this gets simplified down to 3/2, like we just showed a second ago, it would be, this is 4 times 3/2 plus n equals 17. And then it's not so hard at all. The log's gone, and you're just solving a simple equation. And the way I like to solve these is if I ever have a fraction, I multiply everything by that number denominator. So times 2 times 2 times 2. And that would cancel that, and this would become 4 times 3 is 12, plus 2n is equal to 20, 34, and then it's really easy to solve from there. Okay, so what's the moral of the story? You got to be able to handle complicated fraction exponents. That was takeaway number 1. Number 2, you need to learn more about how logs can go together. By now, I'm hoping that this is like the back of your hand. You go, oh, that's equal to what? 3. But even if it's a complicated thing, you can get it simplified down like the square root of 125. That shouldn't take you very long. What's this one equal to? Don't say it, think it. So that's really 5 to the third in there. So this is really all 5 to the 3/2. How many of you had that in your head? Good. So that's all equal to 3/2. Okay. So this whole thing is just 3/2. 3 over 2. All right. But do you know what happens if I have 2 logs like this and I want to put them together? I don't know if you know how to do this yet. When I mean put them together, I mean add them together. Like x plus x makes 2x kind of thing. Like I want to put these 2 logs, separate logs, into just one log. If I was going to make just one log, guess what base it would be? 2. Okay, that's not too hard. There's a really, really simple answer. Want to take a guess at it? 8x. Yep. I want you to think about that. Do multiply and add kind of go together? Let me make you think about that a little further. If I had 9 plus 9 plus 9, isn't that kind of a multiply problem? Add going with multiply. 9 plus 9 plus 9 is 27, but I could have done that by doing 9 times 3. So you get how add can be turned into times? All right, well, in the log world, this is different than normal math. Logs have a whole different system. They follow rules. One of the rules is you can change add into multiply if you want to, as long as the bases are the same. Then that plus that becomes that times that. All right. I wanted to make you think that through by doing something like this. Log base 2 of 4. Everybody write that down. First of all, you should know what the answer is. What is it? 2. Okay, but could I break that into log base 2 of 2 times 2? I mean, isn't that the exact same thing? I just swapped out the 4 for a 2 times 2. So then, isn't that, from what I just told you, able to be broken into 2 logs. Log base 2 of, and then what are these logs? They're added together. Log base 2 of what? I'm breaking this up. 1 goes here, 1 goes there. Log base 2 of 2 plus log base 2 of 2. Isn't that just equal to 1? Plus, isn't that just equal to 1? And 1 plus 1 is equal to 2. And you just told me a second ago that this was equal to 2, right? Okay, and then how about this? If these are identical, which they are, then can't I just say I have 2 of them? 2 log base 2 of 2's? And isn't that also equal to 2? Because isn't this really equal to 1, and then 2 times 1 makes 2? Whoa, so many ways you can do this stuff. Okay, and then I have another one. Couldn't I break log base 2 of 4 into log base 2 of 2 squared? And then, this is something you've never been told, but maybe you can figure out, where can that 2 go? To the front. Because then it'll look identical to this one. Now it's not here anymore. And it's still equal to 2. Because it's 2 times, that's equal to 1, so it's equal to 2. All right, so what's the main new thing for today? This. You can take something that's multiplied and break it up into an add, or even more powerful, you can take something that's an add, log base 2 of 8, and you can put them together. And I just did this one a second ago, and if you have a modicum of a short-term memory, you'd be able to say it was log base 2 of what? 8x. Okay, now why would that be handy? Because what if it equals log base 2 of 16? Ooh, so log base 2 of 8x is equal to log base 2 of 16. And logically, if these are the same thing, then these must be the same thing. 8x must equal 16, and therefore us x have to equal 2. All right, let's see if you really caught that. I think some of you did really well. Others were kind of staring with a lost look in their face. So let's try one. Log base 2 of 7 plus log base 2 of 2x, yes, I'm going to make it a little more complicated, is equal to log base 2 of 28. Solve. Hint, put the left side together. Then, you're not really canceling the logs, but you get the logs out of the picture by saying the arguments must be equal. And then you just solve it, and then the answer is x is like 7, except it's not. I'm going to pause for a second while you give that a try. I hope you knew how to put these guys together and say log base 2 of 7 times 2x. Wouldn't that also be known as 14x? Okay, equals log base 2 of 28. Now, I'm not the one who told you that these cancel, because they don't really cancel, but it's kind of like they cancel. See what I mean? Then it's 14x equals 28. And if you can't solve that, please go back. Go. Do not pass go. Do not collect degree. Or the $200, yes. All right. Okay, so again, this isn't really canceling, but what's really happening is if these are the same, then these must be equal. So I write a new equation with them. Say being equal, and it's easy. Okay, but what if it had come down to this? And I know some of you guys are going to be like, what just happened? But I think some of you will be able to do it. Put the 2 on the left together. You can never solve this until you get it down to 1 log on each side. Because as soon as you get it down to 1 log on each side, the logs can come out. And you just have variables left, and you can just solve an equation. But this is one from like 3 units ago. Do you still remember? how to solve things like that? We'll find out. I'm going to pause for a second. Okay, let's get started. Log base 2 of x plus 4 times x minus 3 equals log base 2 of 8. And these are not canceling, but that must equal that. So I'm going to rewrite that as an equation. X plus 4 is x, or times x minus 3 is equal to 8. And can I just say the answer is negative 4 and positive 3? No, because it doesn't equal 0. 3 didn't do anything except make this side equal 0, and then that's wrong. 0 is not equal to 8. You know what I mean? So we got to multiply it all the way out. Did you get x squared plus x minus 12 is equal to 8? And then I got to subtract 8 from both sides. X squared plus x, subtracting 8 is equal to negative 20 equals 0. Oh, that's a pain. Doesn't seem like it would factor, but it does. Raise your hand if you figured out that it factored. Sweet. If you didn't know that it could factor, then at least know this. If you can factor it, you should, but if you can't factor it, you could always quadratic formula. Know that. If they won't factor, it's not like you're stuck and you can't do it. You just use quadratic formula. Quadratic formula, x equals negative b plus or minus square root b squared minus 4ac all over 2a. And if you want to know quick whether it's going to factor, did you know this? That you could just do the b squared minus 4ac part, and if that part works nice, then you'll have a factor. I don't know if you ever caught that before, but I thought I could throw it in as a value added today. B squared minus 4ac, where b is 1, so 1 squared is 1, minus 4 times a is 1, times c is negative 20. I don't know if you ever knew that if this works out to be nice, like 81, which is what it does work out to be, if that works out to a nice number, as in something that has a nice square root, then it must factor. But to find those factors, you still have to finish the whole x equals negative b, which is negative 1, plus and minus the square root, all over 2a. Kind of fast forwarded through the song there, but. And then that's negative 1 plus and minus 9 all over 2. And then negative 1 plus 9 over 2, negative 1 minus 9 all over 2. And those are the two answers. Those are the things that it would have factored to, which is 8 over 4. 8 over 2, which is 4, and negative 10 divided by 2 is negative 5. So that means x minus 4 and x minus negative 5, also known as plus 5, is equal to 0. So, hey, it does factor. See? Okay, and the answers were 4 and negative 5. How many of you got that far? Wow, I'm impressed. All right. So, it's a quadratic built in the middle of a log problem. Holy smokes. I could see this being a difficult, like problem 53 on the ACT, because it involves two hardcore concepts, logs and quadratics, and they're both right in the wheelhouse of the ACT. Now, I'm not saying this was on anybody's ACT test, but it could be, because those both are listed in the list of things they can test you on. Yes? Ooh, okay. Would negative 5 be extraneous? Let's go back and look. Negative 5, when plugged in the original, does it cause trouble? Yes, it does. Look at that. I have a negative argument, and here I have a negative argument. Both of them turn out to be negative. That's not legal. You can't have negative numbers there. Good catch. I didn't even catch that in my first hour class. Good catch. So that's extraneous. Now, just be careful that you don't think that every time a number is negative that it's like extraneous. It's not true. You have to stick it in the original and see if the original makes that number. Because see, like if this had been a plus 17 here, then negative 5 plus 17 wouldn't have caused a problem. Because the whole thing would have to be negative. And this number was small enough that it was a problem. But if this number here had been bigger, again, if this had been like a plus 18, and this had been like a plus 20 or something, then it wouldn't have mattered that we had a negative answer, and it would have still worked. So don't just get it stuck in your head that negative answers never work. When you put them back in, you got to see if it causes a negative argument or a negative base. Okay, and that's not even the end of it. There's even more that I want to prepare you with about logs. Okay, first of all, we graph them. Do you know what the parent log looks like? What if you went brain dead on the test and you're like, I can't remember what this looks like. We did so many different things. We did exponentials, we did exponential growth, we did exponential decay, and now I'm supposed to remember this log, and I don't remember. What'll save your day? XY chart. I'd like you, crying won't work. We'll just feel bad for you and still mark it wrong. All right, let's not use log base 2. Let's use log without a base and see if you know what that would mean. Would you please find 3 points that are on this and the asymptote, and then make a sketch. 3 points that are on this one. Some of you are like, what? How can it not have a base? Well, then it has a base. It's just base what? False, not base 1. What is the most common log? There it is, base 10. If you don't know what the base is, that means it is the most common base, which is base 10. That's what your calculator uses, base 10. If you didn't know that, you just learned something important. Okay, so log without a base means that it's the shortcut. When you use a shortcut, something you use all the time. Like square roots. When you were doing square roots in middle school, they didn't even write this. Even though technically there should have been a 2 right there, but they didn't even write it. Why? Because you write so many of them that there's a shortcut, and that is the most common square root is the one that's a cubed root, or sorry, square root. If they had shown you like cube roots and fourth roots, they probably would have written it in there, but they were only doing square roots, so it's a nice shortcut. If you say that, you mean that there's a little 2 here, but you don't have to write it. The point is, if you don't have a base, then you do have a base, and it's base 10. That is called common log because it's the most common log. Okay, now that you know the base is 10, I hope some of you, just to prove my point, plugged in a random number like 2 and said, okay, I'll stick in 2. You gotta use strategery. 2 was not a good choice. What was a good choice? Wait a minute, 0? You can't have 0 here. 0's not allowed. 1. Ooh, I like 1 because then I can say my dumb little saying. What's my dumb little saying? You won the argument and you get nothing, 0. If you don't remember that, how are you supposed to solve it? Well, you go like this. You say equals x, because I don't have a variable anymore. And I go 10 to the x equals 1. Remember the whole rewrite? And then I go 10 to the what is 1? Oh, x must be 0. In case you forgot the 1 the argument is 0 thing, you can solve it and figure it out that it's 0. Cool, 1 comma 0 on there. Use strategery. 10. 10's a good choice. Because log base 10 of 10, that's easy. It's 1. Put in a 10, I get a 1. And then we have the middle child option, always overlooked. 1/10. 1/10 is a really good choice. Everybody forgets to try that, but it works really well because it's the same as 10 to the negative 1. That means when you put in 1/10, then this becomes log base 10 of 10 to the negative 1, so the answer is negative 1. 1/10 gives you negative 1. That's the one most kids aren't going to know on the test. They'll be able to do the 10. They'll be able to do the 1, the argument thing, but they'll forget to put in the fraction. And then they'll be like, how am I supposed to get a 3rd point? Because it won't fit on the graph. When I put in like 100, I can't graph that. And I'll say, try to think of another way. All right. So you use, if this had been log base 7 of x, what would have been the 3 smart things to put in? 7 would have been worked well. What else? 1 works well, and what else? 1/7. Okay, good. You got it. Okay, now we graph this thing. And I hope you know the asymptote runs down here on these. And remember me saying they kind of look like a tree blown over in the wind, because that's what a log is a tree that's been blown over, and then they cut it up in chunks. Okay, anyway, that's how they kind of look. Now if I graph these actual points, 1, 0 is here. 10, 1 is way over here. Is that right? Yep. It's making a very sharp turn because it has a high base. The bigger the base is, the sharper the turn is. It's not a nice, easy turn. It's a sharp turn. And then this last one is over 1/10 and down 1, which is about there. So there we go. There's my graph. Do I have 3 points in the asymptote? Okay, good. Then I'm good. But wait, it wouldn't be that simple, would it? I mean, really, for an honors test, not likely you're going to ask you to just graph log base 10. What could we do to it that would be kind of easy? Move it. How far? Like 1 to the right. How would I do that? Like a -1. That would move it 1 to the right. What could we also do? Like move it down 5. Wouldn't that be still pretty easy? But what would be something that would totally change how this graph looks? Stretches aren't that hard. If I stretch it and make it twice as tall, it just looks like that. It looks very similar. Ooh, make it negative. He's on a fire today. What did you eat for breakfast this morning? Okay. Live goldfish? Live goldfish? It's a lot of protein that way. Okay, all right. Anyway, so if I put in a negative on the outside, I'd like you to sketch what you think this thing looks like now. Granted, you could go through and find points, which is the for sure way, but just give me your gut. What should this kind of look like? A lot of people do it wrong. You got to flip it, but do you know what it's going to look like? Here's the mistake answer. People go, okay, so he wants me to flip it over this. So there, I flipped it. It's not right. It's kind of close to right, but it's not right. Let me show you the difference. This part was fine. See what I'm saying? It needs to flip over the line just as far as it was above the line. Now that's how far it is below the line. See what I'm saying? Ooh, fishtail. I like it. Absolutely. Because the XY chart is your best friend. So you still, in fact, I'm going to leave those X's there. I'm just going to get new Y points. So if I put in a 1 right here, do you get that that's, oh, I won the argument, I get 0, and it's still 0. Do you get it still goes through here? And if I put in a 10, it's still equal to 1, but then I times it by the negative, which makes it -1. That changed. So over 10 and down 1, ooh, I see, it's down there. And then last but not least, 1/10 goes in. 1/10 goes in, and then I get -1, but then I times the -1 by a negative, which makes it +1. So that's up here. And look at that. Here's my 3 points, and they're on that line, and that would have saved the day anyway. But you need to understand what they look like when they're upside down. All right. Do you remember on the last test, we gave you a graph? And if I remember right, the last test, it was like exponential growth or decay or something. Let's say it's growth. And it was like this, except it was like moved down and stuff. So how are you supposed to do this again? A lot of people forgot what I've said 1,000 times by now. What's your best friend in graph? XY chart. You have to have the XY chart. And you're like, but you don't tell me any numbers. Yeah, we do. If we gave you a graph, we told you numbers. And what should you do with those numbers? You take those numbers and you put them in the chart and you see if they work in your formula, your equation. And the kids that had the wrong equations, I could tell they hadn't checked the points in it. If you stick the point, let's say that the point is like, let's say this one here, it's 0, -3. If you stick 0, -3 in your equation and it doesn't work, then your equation's wrong. You know what I mean? You can tell your equation's wrong, and you have to go, okay, well, maybe I didn't move it far enough, or maybe I didn't flip it the right way, or maybe I didn't, you got to guess and check your way until you got the right equation. And then you'll know, because when you stick the points in your equation, it'll work. Okay. Your homework for tonight is one of your favorite things. It's a Schoology quiz. So let me get the first couple with you. I know it's getting close to the end. I get that. But you might want some free answers. If nothing else, maybe you should write this. Don't move. Don't move. Because then you won't hear anything. Sit down. Okay. I am going to give the first couple of answers here at the beginning. I would recommend that you write them down. You're your own person. You can do what you want. But this will be something I'm going to put in the grade book. So I would recommend doing it. Okay, so the beginning one, it looks super complicated, but it's just a rewrite. Don't forget the rewrite process. 64 to the 1/3 is equal to x minus 7. And then if you know what 64 to the 1/3 is, this becomes baby talk. It's super easy. It's just 4 equals x minus 7. See what I mean? You can transform something that looks super complicated, and as long as you know this is 4, then it's super easy. 4 equals x minus 7. Another thing that looks really scary, but it's not. If you rewrite it, 4 to the x equals 16 to the a. And I hope you're getting, oh, I wish I had the bases the same. I'll rewrite the 16 as a what? 4 squared. Does this ring a bell? You had a test on this, just like this. All right, there's the first couple. Have your homework done. All I got for you for today.